Alright, so we're going to define the biconditional. So this is formally defined as P if and only if Q. And that's going to be logically equivalent to the conjunction of two conditional statements. So if P then Q and if Q then P. And again, we say that P if and only if Q. Sometimes we'll abbreviate with IFF. And remember that this is a conjunction, so if we're trying to show it on a truth table, we have to show if P then Q, then we'd have to show if Q then P, then we would have to show the conjunction of the two. So for the truth table, we'll bring in just the conditional down there. On the left we have the antecedent, the consequent, and then if antecedent, then consequent, instead of using P and Q, just for reference. So first P and Q. Next, we want to do if P then Q. So we know that's going to be true, false, true, true. Next, we know that we're going to have to do if Q then P. So here the antecedent's Q, the consequent is P. So we're looking for Q to be true, P to be false, and that's where it's going to be false. The rest are going to be true. And now we can do the conjunction of the two. And remember that a conjunction is only true when both are true. So that happens at the top and the bottom. And so here is our truth table for P if and only if Q. And two definitions. A tautology is a statement that is always true, and secondly, a contradiction is a statement that's always false. So for an exercise, try showing that this thing right here is a tautology. P and if P then Q. That's going to be the antecedent, and then Q is just the consequent. So if P and if P then Q, then Q. Alright, so using everything that we know about logic and sets, we're going to start proving mathematical statements. And so usually they're going to be in the form if P then Q, or P if and only if Q. And in the next chapter, we're going to prove pretty complicated statements. But for now, we're just going to look at a vacuous and a trivial proof. But before we do that, this is a typical statement that we'll see. So we're going to use logic, even the truth tables, and we can come up with all the cases where a certain statement's going to be true. So this conjecture right here is saying if n is even, then its square is even. And we want to just test that out a bunch and see if it looks like it's actually going to be true. In this case, it does look like it's going to be true. And so now we would go on and try to prove this thing. And since it's of the form if P then Q, we assume P is true, and then we show that Q follows from P. So Q is what we're after we assume P is true. Alright, so for reference we have our conditional truth table. And notice that whenever Q is true, the entire statement if P then Q is true. So again, whenever Q is true, if P then Q is true. So if we try to prove a statement that way, we've done so with a trivial proof. And if we shift that down, whenever P is false, if P then Q is true. Those are the last two cases. And if we prove a statement this way, we're proving it vacuously. Alright, so we're going to do two examples. The first example, if we let x be a real number, then if x is less than 0, then x squared plus 1 is greater than 0. Now we know that x squared is always positive, or 0. And so if we add 1 to that, it's going to be greater than x squared. So we can say that x squared plus 1 is greater than or equal to x squared is greater than or equal to 0. And that means x squared plus 1 is greater than or equal to 0. And that's our proof. Basically, we just show that Q has to be true here. Q is always true, and P could have been anything, and that's what makes this a trivial proof. Secondly, x is a real number, and we're going to say that if x squared minus 6x plus 9 is less than 0, then x cubed is greater than or equal to 8. Notice we can factor that. And if x minus 3 squared is greater than or equal to 0, that P statement is going to be false. So the fact that x squared minus 6x plus 9 is less than 0 is impossible, and therefore false. Makes it so that we don't really care what that second then statement is, the Q statement. And that makes this entire thing vacuously true. So these take a little bit of time just to kind of stare at and compare with the truth tables, but they're not so bad. They're a lot simpler than we actually think they are, so we don't want to overcomplicate them.